Okay, good. So it's our great pleasure to have today's seminar speaker, Professor Kunihito Yuka. So Ioka-san got a PhD in 2001 at Kyoto University, and he became a postdoc at Osaka University, and he did a postdoc at Penn State University, the work with Peter Mader. And he became an assistant professor at Kyoto University in 2005, and became an associate professor in 2007 at KK. And then he became a full professor at Kyoto University in 2016. So Ioka-san had worked on many different subjects. Actually, in the early days, he worked on the binary formation of black holes and gravitational waves from the multi-binaries, the magnetars. And he actually also started to work on the gamma ray bursts and different kind of transients and cosmic rays and the other transients of the also related to high energy. So he received the Young Scientist Award from Japan Physics Society, so for gamma ray bursts, and he actually also recently interested in the fast radio bursts, and he actually contributed to work on he proposed some cosmic dispersion measure to use cosmic probes. So today he's going to talk about the fireball in the fast radio bursts. Thank you very much.
Thank you very much. So let me read my last thought. So today, thank you very much for giving me a chance to talk on fireball in the fast radio bursts. And this is a collaboration with my former student, Yukawa, and my postdoc, Wataru Ishizaki. And so fast radio bursts are mysterious transient with extremely high brightness temperature. The brightness temperature is about 10 to minus 32 to 36, and the duration is about milliseconds, and the flux is about Jansky level. So you can see this extremeness by using this figure. This is the duration on the horizontal axis, and this is the spectral luminosity. And you can see these points of FRBs, and so duration is about millisecond, and luminosity is about Jansky level. And this is much brighter than pulsars in our galaxy, and this is much shorter than the gamma ray bursts or AGN flares. By using observations, so you can measure the intensity and the frequency, and putting these quantities into this equation, you can obtain the brightness temperature. And by using millisecond and the distance of gigaparsec, and the flux is Jansky, and the frequency is gigahertz, then we have about 10 to 35 or even higher temperature for these transients, FRBs. So this is very extreme events, and people consider that most likely emission is due to the coherent emission. And so this is a simple explanation of the coherent emission. The power is proportional to E to square. So this is a electric field. So usually phase of the electric field is random. So if you multiply the sum, then the cross term usually drops. And then power is proportional to the number of particles. And this is the incoherent emission. So power is proportional to the number of particles. But in the coherent emission, this term is important. So combination of is proportional to n square. So coherent emission is much stronger than the incoherent emission. In addition to these mysterious aspects, so there is a very interesting features in FRBs. So this is an observation of FRBs. So frequency, and this is time, and you can see that the signal has a dispersion, so-called dispersion. So higher frequency comes earlier and the lower frequency comes later. So delay time is proportional to nu to minus 2. And by using this feature, we can measure the so-called dispersion measure. And the dispersion measure is a column density of free electrons, and usually expressed in this unit. And if you additionally measure the redshift, you can plot like this. So redshift as a dispersion measure as a function of the redshift. And if you fix some one cosmology, so one universe, so some cosmological parameter is fixed, then you can plot this line. And so dispersion measure is a column density of electrons, so it increases as redshift increase. So by using this, we can measure a kind of distance by using the dispersion measure and the redshift, so distance, redshift relation, something. So similar to supernova 1A. And maybe by using FRB, we maybe do a new cosmology, so-called FRB cosmology in the near future. And so recently, 2020, so there was a detection of galactic FRB. So in our galaxy, usually FRB is an extragalactic phenomena, but this is a galactic FRB. And also it was found, it is from Magnetar bursts. So this observation is very important and provide a smoking gun that one of the origin of the FRB is a magnetar. And this is flux, and this is time, and this gray line is the X-ray light curve. And this orange line is so FRB. So associated with X-ray burst, there was 2 FRBs, and from our galaxy. And X-ray luminosity is much greater than the FRB luminosity. So this means that so this phenomena is so main phenomena is X-ray burst. So magnetar X-ray burst. And FRB is a kind of...
This particular magnetar was slightly fainter than the other extragalactic ones, right? This magnetar, this FRB.
So magnetar is so sometimes bright, sometimes faint.
This particular one was fainter than the most other extragalactic FRBs, no?
Oh, right. This FRB is very faint. Actually, so this is this galactic FRB. So it is fainter than the extragalactic FRB, but it's 2 orders of magnitude or something like that. So people consider that it's a kind of
understood by some selection effect, or is this supposed?
People consider it's a kind of selection effect. So it's so in our galaxy, event rate is not so high. And the luminosity function shows that the fainter bursts have more numerous. So usually we expect some more so fainter events will occur typically in our galaxy.
So for this one, we see these 2 pulses. It is typical in other fast radio bursts.
Oh, sorry, I forgot to mention that. So there are 2 types of so phenomenologically 2 types of FRB. One is a repeating FRB, and one is a one-off FRB, so single FRB. And currently, so about 1,000 single one-off FRBs are detected, and repeating FRBs about 20. So the number is 20. So currently there are many discussions about whether these 2 FRBs are same category or same species, but we have not yet the answer. So this is a kind of repeating FRB. Yes. So what should I say? So yeah. So according to this observation, so Magnetar is one of the origins. So we consider in the following this kind of scenario. So Magnetar scenario, and even in this scenario, there are still large uncertainty. So especially the emission region is not yet determined. So one is, so this emission region is broadly classified into two regions. One is in the magnet sphere. So the size is about less than 10 to 10 centimeter. On the other scenario is a wind-like, gamma-ray burst-like model. It is far from the source and even beyond the AU scale. So, but today I would like to ask another type of question. So the question is how to transfer the energy from the surface of the magnetar to the emission region of the FRB. So, so usually people consider that the energy source is a kind of magnetic field because a magnetar is slowly rotating and rotational energy is not so large. And magnetic field is a dominant energy source. And also the energy is concentrated on the surface. So something happens near the surface. And on the other hand, FRBs should be generated far from the surface. Otherwise, FRBs, so radio waves cannot escape from the surface due to some interaction. So we have to transfer energy from here to here. And there are basically two types of transfer of energy. One is Poynting flux. So usually people use Alfven waves. The other is kinetic flux. So plasma inertia brings the energy in from the surface to the emission site.
How far is the emission site? You said it was very far, but roughly speaking.
Roughly speaking, here to here. So nobody knows. So, but people usually think above 10 to 7 to 10 to 8 centimeter, and but up to 10 to 13 centimeter. So we don't know. So. So here, first, in the half of my talk, I would like to concentrate on the kinetic flux. So this is a kind of fireball. And on the other half of the talk, I would like to consider the Alfven wave. So as I said, so this phenomena, so Magnetar flare is a dominant phenomena. So energetics, so Magnetar flare is dominant than the FRBs. So for the Magnetar flares, the most famous scenario is a trapped fireball model. And in this scenario, some energy is released near the surface, and this produces E plus minus pairs. And this is trapped by the magnetic field like this. And the size is determined by the luminosity and the temperature. And for given luminosity and the temperature in this event, so galactic event, its size of about 10 to 4 centimeter, much smaller than the neutron star size. So, but in this galactic event, So this trapped fireball model does not work. So the reason is its high temperature compared to other Magnetar flares. So temperature is about 80 kilo electron volt. And in contrast to usual Magnetar burst with 10 kilo electron volt. So given this high temperature, we can calculate the optical depth of the fireball at the surface. And we can show that optical depth at the surface of this trapped fireball is much greater than unity, and at this 80 kilo electron volt. For usual burst, optical depth is much smaller than unity. However, in this case, optical depth is much higher. So this means if the photon tries to escape from the surface of the trapped fireball, so then this photon can create E plus minus just outside of the initial trapped fireball. So this is possible due to the X-ray tails. X-ray itself cannot produce E plus minus, but there is a tail, and the tail creates E plus minus. And then if the magnetic field is closed, then initial fireball just expands like this. So then this contradicts with this relation. So for given luminosity and temperature, its size is about this. But if the outer field is closed, this optical depth is much larger than unity, so then it becomes too big. So the solution is that outer magnetic field is open, not completely open, but so open at some distance. So and then so E plus minus can expand along the magnetic field, and due to the expansion, density decrease, and so thermal energy can be released at some point. So because the density becomes decreased sufficiently.
For the ordinary burst, like is the time period much larger, or do you not detect it in radio at all?
So far, so you mean the previous X-ray bursts?
Yeah.
No.
When you distinguish the ordinary versus these FRBs, the time period is the distinguishing factor, or just the emission in radio?
No. So this is your question is.
I was just trying to distinguish this ordinary burst versus this.
So only this temperature and FRB. Difference is temperature and FRB. And so expanding fireball can release photons, and by decreasing the density and releasing the X-rays. And this is a kind of fireball similar to gamma ray burst. In the gamma ray burst, so initial fireball temperature is observed as the observer. This is because due to the expansion, so temperature, so co-moving temperature decrease due to the adiabatic cooling. On the other hand, due to the expansion, so thermal radiation pushes the plasma, E plus minus radiation plasma, and it accelerates due to its own radiation pressure. And Lorentz factor increase like this, and the observed temperature is blue shifted by this Lorentz factor, and then temperature is keeps the initial temperature. This is a usual gamma ray burst. In this FRBs, so field is a kind of dipole-like configuration. So evolution is slightly different, but the same relation is satisfied.
Is the Lorentz vector the same as the regular gamma ray burst?
I will show you later. And so if the initial size of the so energy release is something like this size, then we can explain the temperature of the X-ray radiation. So given that relation, I would like to ask, what is the kinetic energy of the E plus minus outflow? So my question is whether this outflow has sufficient energy or not to explain the FRBs. This is a problem in the first half of my talk. So we have to consider something, for example, baryon loading. So this is luminosity is much larger than Eddington luminosity, so baryon could be loaded at the base of the magnetic field. Then baryon is very important for the evolution of the fireball because there is electrons associated with baryon, and this electron does not annihilate. So number does not decrease exponentially. It just decrease power. Also, electrons provide the scattering, and it's very important for the acceleration of the fireball. And in addition, there is a escape of photons. So usually in the GRB context, we only consider the simple photosphere. And if the optical depth becomes less than unity, the photons can escape. But in this setup, we should consider the diffusion laterally across the magnetic field, and this diffusing photon can produce E plus minus, and E plus minus can annihilate and escape to photons can escape like this. And we consider such a this process, and final summary is something like this. So this is radius. And this is dimensionless entropy. So right hand is baryon poor, left hand is baryon rich. And usually, so this is E plus minus fireball. This is baryonic fireball. And for given baryon fireball expand, and at this radius, diffusion time scale becomes shorter than the dynamical time. This means that the photon escaped from the fireball at this radius. So, and so fireball basically can be accelerated to this Lorentz factor. And if you have much more baryons, then Lorentz factor can be accelerated up to this radius and up to this Lorentz factor. Basically, Lorentz factor is increased as a function of the radius. So, but in addition to this acceleration, we will show that the further acceleration is possible because even above the photosphere, so the particles receive photons from the photosphere. So radiation still exists, and matter receives photons. So even though it is already our optical depth is less than unity. And so if the work done by the radiation is larger than the less mass energy, this can lead to the acceleration of particles. And for example, if you consider Thomson scattering, then this condition, with this condition, these particles can be accelerated further, even above the photosphere. And then the Lorentz factor increase as a function of the radius like this. And at some point, this equality does not satisfy, and so decoupling happens, and Lorentz factor stays constant. And in addition to the Thomson scattering, so there is also a resonant cyclotron scattering in this setup. So there is a magnetic field, and the particles are moving around magnetic field, and a photon comes, and at some resonant, so cyclotron frequency, resonant frequency. So this, so cross section becomes very large, and this even enhance the acceleration further like this. So according to this resonant radiative acceleration, so fireballs can accelerate up to this Lorentz factor. So Lorentz factor can be up to 100. This is a main conclusion. And so regardless of the baryon fraction. So we can also calculate, so given fireball evolution, we can calculate the kinetic luminosity, and for each component, so E plus minus, and this is baryon outflow, and this is E plus minus outflow. This is dimensionless entropy, baryon poor and baryon rich, and this is normalized by the initial luminosity. So if the baryon is so this parameter eta is less than 10, then almost all energy goes into the kinetic energy. And if the baryon is very few, then so luminosity is about 10 to minus 4. And this is not the observed quantity. The observed quantity should be corrected by the opening angle and beaming, relativistic beaming. By correcting these, by these corrections, we can convert the luminosity, true luminosity, to isotropic, so-called isotropic luminosity. Then we compare the observation. Observation suggests that X-ray and FRB luminosity is about, the ratio is about 10 to minus 3. So kinetic energy should be larger than this line. And we can see that if there is a baryon, so it's easy to achieve this. And even if there is no baryon, it's marginally, so it's only by a factor of 2. This model is not so accurate, so I think that it's still possible. And so the conclusion is the isotropic kinetic energy can be larger than the FRB. So
what is the dependence on magnetic fields? I think if you put a strong magnetic field, the cycle resonance more important, right?
Right.
I think the Lorentz factor can be more pushed.
yeah,
So that you can actually, it means that they probably, in this case, maybe 10 to 14, it's relatively conservative, but if you use a 10 to 15,
right.
the gamma is probably larger than maybe the full X-ray one, they might be.
Yes, that's right. Yes. But in this event, so magnetic field is a kind of measured, right. So 2 times 10 to 14 Gauss. And I'm using this value, but yes, as you say, so there are many assumptions. The magnetic field is dipole field, and also the yes. So magnetic field measurement is only through the dipole, using the dipole formula, and so there are many uncertainties. And this is, I think, considering such an uncertainty, this is still possible.
So it is fair to say that if we don't assume any magnetic fields, as a cyclotron resonance happens, if you ignore this, so baryon poor, no way. Is it true?
No way. Yeah, I think so. I think so.
So cyclotron resonance is crucial.
Very crucial. Yes, that's right. So
That blue line that corresponds to again the galactic one. The
galactic one. So observed one.
ones would be 2 orders of magnitude.
Yes, that's right. So conclusion in the first half of my talk is that fireball that explains the X-ray burst can also produce outflow with sufficient energy for explaining FRB. So this is the first conclusion. And the important agent is the baryon or resonant scattering. Okay, let's consider the next box.
So in this scenario, would you expect it to repeat? Since in this one, it will repeat again and again, right?
Right. If you inject energy at the surface,
yes,
then it will produce fireball. And if you repeat the energy injection, and second fireball happens.
Whereas observationally, well, there have been 1 or 2 which repeat, but not all of them, right?
Right. And also the fireball position may be different. So I don't know. I cannot say sure. Yeah.
You have to assume something about the numbers of pairs you have, or is it?
It is fixed by the temperature. So usually it's completely optically thick at the surface. And basically, maybe I have right. So yes, this. So for given temperature, so number density is basically fixed. So this is so this formula is considered the magnetic field rather than the critical magnetic field. So because lambda occupation, so distribution function is anisotropic, and the density of E plus minus is slightly modified from the usual Maxwell distribution. But for given temperature, so number density is fixed in this setup. Okay, so let's consider the next topic.
Sure. So when we talk about repetition, is it periodic or not?
So far, no. So
It's not that within a short period you have some repetition, but I mean, kind of what's the range between time difference between the two?
basically, so people don't consider that so periodicity is observed, so related to the Magnetar rotation. So I will come back later.
So does this scenario predict any like radio spectrum, and can that be compared with observation?
So far, no. I will come. Okay. So next, so let's consider the Poynting energy. On top of the some fireball. So there is so if the energy is released near the surface, so in addition to the thermal energy, there should be some Poynting flux generated. And then here I would like to consider the three-wave interactions. This is comes from the solar physics. In the solar physics, so the Alfven waves are very important for heating the corona, so solar corona, and also the acceleration of the solar wind. In this scenario, so Alfven wave decays into the Alfven waves and acoustic wave. So more precisely, it's a slow wave. This is three-wave interactions. And a slow wave basically makes shocks and dissipate like this. So slow wave can easily makes a shocks and it dissipate. So if this three-wave interaction happens, then the initial Alfven waves lose energy. And the growth rate of this interaction is estimated in the solar physics like this. And this is the frequency of the wave. And the growth rate is proportional to the amplitude of the Alfven wave and the ratio of the Alfven wave to sound wave. And this is very quick if the amplitude is close to unity. So it's close to the frequency of the wave. So it's gigahertz. If you convert to the length, it's centimeter scale. So we are talking about 10 to 8 or 10 to 9 centimeter and even larger scale. So, and if this happens, this is very quick phenomena. But this, so let me explain only by this slide about the three-wave interactions. So this is a magnetic field. This is velocity, and this is density. And the background is some straight line magnetic field. This is background. On top of that, there is a parent Alfven wave. And we consider the daughter Alfven wave and the daughter sound wave. And we treat these quantities as perturbations. And we can write down the MHD equation like this. So left-hand side is a simple linear equation. And the right-hand side is a nonlinear term. Coupling these waves. And the dominant, forget to explain the parent Alfven wave. Parent Alfven wave, here we assume some circular polarized Alfven wave. And if you put such a parent Alfven wave, these daughter Alfven wave and the daughter sound waves are grows up through these nonlinear terms. And picking up some dominant term, we can calculate the using the resonant condition, and we can calculate the growth rate. So from this equation. And however, this is non-relativistic. So in the neutron star, magnetosphere, magnetic field, magnetic energy dominates, and so we have to consider the relativistic MHD, and so we use energy momentum conservation, the induction equation, and equilibrium states, and ideal MHD, and adiabatic equation state, and the magnetic field is is straight, and we consider the waves along the magnetic field and circular polarization, and we consider in the fluid commuting frame. So background fluid is zero frame. In this frame, we can manage to consider the dispersion relation. So this is a kind of simple problem. So we have searched paper relevant to this instability, but we couldn't find so exact paper. So treating this instability. So if you know some relevant papers, please let me know.
So
So
there was a paper which says that the magnetic field itself was remained pretty constant. Now, in this scenario, you would expect that the magnetic field changed by almost a factor of 2, right? Delta B over B,
but this one, so this is parent member, yes.
but the magnetic field in some was not very much. I don't remember the exact.
Okay, so
Okay.
let me tell later. And anyway, so and
Yeah,
sorry,
just a quick one. What's the magnetization for which this works? I guess you might need a lot of baryon loading, right?
so you mean the sigma parameter?
Yes.
Yes, this is, I will write down the formula by using this parameter, yes. And we consider the sigma is rather than unity.
Okay, unity, okay.
And so there are several papers considering in the force free, and but the force free case kills the slow mode. So the slow mode is very important for this instability because the sound wave is slow mode. And so the strategy is the same. So we consider background field and the parent wave and daughter wave, the sound wave. So and we only consider the coupling. And so this is very complicated. So but it's straightforward. And we write down the relativistic emits equation into the quantum equation. And here, as pointed out, so dimensionless parameter, so sigma parameter, so energy density of magnetic field to the matter, this parameter is very important. And also this parameter, so sound wave to Alfven wave, velocity ratio is very important. And after so Fourier transforming these equations, we have resonance condition, and takes a determinant of 6x6 matrix equals 0. Then we have a dispersion relation. This is very complicated. Actually, here S0, S1, S2 is a complex function of K and omega. And but we can take a limit, for example, non-relativistic limit, and then this dispersion relation reproduces the previous results, something like that. And this reproduces so previous equation. So this is the equation for the solar physics, and the instability happens on the time scale of the wave frequency and times the amplitude of the magnetic field and the ratio of the Alfven wave and the sound wave.
How important is the circular polarization to get there of the Alfven waves?
Circular polarization.
Is it important to get to this result?
So I'm not sure, but so far I have done for the circular polarization only. So this is the easiest of this. So and yes, but if you consider the E plus minus plasma, then maybe normal mode is can be chosen by the circular polarization. So I guess the same conclusion is obtained, but it's still speculation. Hi, yeah. And we can also take the high sigma limit, sigma to infinity. And then we obtain this equation, and this equation does not have imaginary solution. So no instability, so consistent with the force-free analysis. In the force-free analysis, sigma is infinity. And in the force-free limit, so basically magnetic degrees of freedom decouple from the matter degree of freedom, and Alfven wave is basically stable. plotting the previous dispersion relation in the figure like this. And we found that this is numerically plotted. And this instability happens right around here. So this is a sound wave dispersion relation. This is a K wave number, and this is a frequency omega. And we can see that there is an imaginary part appear here as a resonance condition. And at this point, we can expand and obtain the growth rate of the instability. And this is a final conclusion. So growth rate is almost the same as a non-relativistic case, but there is a additional factor, sigma to minus 1/2. And so this means that even for very high sigma, this instability persists, but suppressed by this factor.
Does it help you that delta B over B is growing as the Alfven wave propagates out?
Yes.
Okay. So then basically you're saying
I have a slide. So sorry. Oh, this one. Yes, for given luminosity of the FRB, we can estimate the magnitude of the delta B. And so background magnetic field is the Magnetar's magnetic field. So we can estimate the amplitude of the delta B over B. And but it depends on the radius. And if you consider on the surface of the neutron star, it's very small perturbation. But if you consider as around 10 to 9 centimeter, it's around unity. So perturbation is good below this radius. And so if there is a Alfven wave perturbation at the surface, it propagates to the upper atmosphere. So basically amplitude grows according to this equation. So even if initially very small perturbation, it grows as radius increase. So this means that as a wave propagate to the upper atmosphere, then this instability becomes much more and more important, because this factor becomes larger and larger.
Is it known what limits these instabilities?
So far, no. So this equation is obtained in this limit, sigma much larger than unity, and temperature. So temperature ratio is much less than unity. At this stage, so instability remains. So, but it is suppressed. If sigma is very large, so growth rate is very suppressed, but still prevail.
Are there nonlinear effects that can damp the instability?
Yeah, it could be, but this setup, so MHD and ideal MHD, and so just Alfven wave propagate around the magnetic fields and it becomes unstable.
What about in the non-relativistic case? Is it known what limits the instability?
Yes, so this is a solar physics case. So non-relativistic case is growth rate is written like this, and we have reproduced this relation taking the non-relativistic limit and same results.
But eventually saturate. Saturation happens.
Right.
Saturation.
Oh, this is of course linear analysis.
Right.
So if the perturbation grows, then it becomes a nonlinear saturation. Yes, yes,
Right.
that's right.
This will have probably presumably delta B equals to B, right?
Right, yeah. And so from now, this is speculation. So far, linear analysis. And so dispersion is nonlinear analysis. So this is speculation, but if the energy is released near the surface, maybe fireball will produce. And also magnetic field perturbation also produced and propagate. And and the magnetic field energy, Alfven wave energy, could dissipate into the thermal energy of the fireball. And fireball can accelerate by using such a thermal motion, converting the thermal energy into the kinetic energy. So eventually, so some aligned flow could be produced. And I have not considered the final outcome. So it may produce some two-stream instability among these outflow, or this outflow could get out of the magnetosphere and may shocks outside the magnetosphere. And areas showed a very interesting simulation of the Osprey simulation. And if such outflow pushes some currency, then it may produce some reconnection, and so magnetic island could produce some radio emission. I don't know. So far, I have just said that if the energy is injected near the surface, that is converted, that can be converted into the kinetic energy. Okay, so just a few words about the periodic FRB. So some FRBs are some repeating, and FRB comes, so many FRB comes. So if you fold, so this is special FRB. If you fold the signal by using this period, about 16 days, and if you fold, so then the FRBs comes in some window, phase window. And this is phase one, this is phase two, and only FRB comes in this window. So this is a rare event. So only this and this. And, so far, periodic FRBs are observed only for 2 events, and among the 20 repeating FRBs. So this may be rare, but we propose that this may be a binary, and so this period could be the binary period. And if you consider such as configuration, so there is a company star, and it emits some wind, and this is a FRB emitting pulsar. And if the wind exists, so FRB signal is blocked by this wind. So FRBs can be observed at some direction, only to some direction. So if the binary rotates, and this observer sees some periodicity. Okay, so I have the slides, but skip. And so in this talk, I talk about the expanding fireball, and also the decay of Alfven waves. And maybe some outflow is produced. So that outflow could be relevant to FRBs. And finally, I touch and mention and the periodic FRB, it may be finals. Oh, that's all. Thank you very much.
Thank you very much. Okay, is there any questions?
Yes.
For the binary case, so they're basically assuming that the FRB emitter is sort of constant or something, and then the periodicity is just from the orbit.
Yes, yes.
So what do you think produces the almost constant FRB emission over 60 days?
Yes, this is a kind of assumption. So FRB is emitted basically, so isotropically, but some beaming or I don't know, but so and this periodicity, so selection, so no FRB amount, so in this window that is blocked by the wind from the accompanying part.
Sorry, I didn't understand. But these are pulses, these FRBs, so they are.
Yes, but I'm basically wondering if you just constantly emit those pulses and what would basically do
Do
that.
you see many pulses in each of the periods? Because presumably this opening angle of the wind is not so small. Yeah. How do you see multiple FRBs each of the?
So this is folded signal. So observation is much longer than this period, and each period there is no clear periodicity. But if you fold the signal, then this is observed.
So every 16 days you get FRBs, but do you get many FRBs every 16 days for a few days, something like that? Or
Few, yeah.
few FRBs.
So one cycle only one or even zero, and
So for these periodic FRB, so presumably these pulsars or magnetars that are very large stars before. So at this period, they're actually pretty close to the pulsar source. So does that? So I'm just curious, can that survive after that, like common envelope phase?
yeah. So there is some how to say, I forgot the English name, but population synthesis. So yeah, population synthesis code, and that can predict some number of binaries. And such a system is consistent with this scenario. So event rate is consistent. So some guys are discussing about whether this scenario is consistent with event rate of such a FRB or not. And they discuss. This is not so peculiar.
At the very beginning, you showed the X-ray and FRB. Why there's a delay of X-ray or FRB? X-ray is delayed, right?
Yeah, this is debatable.
Yeah. Also, like,
according to this paper,
one.
the FRB comes fast and
Right.
slightly delays the X-ray.
Right. So
Yeah.
we understand why.
Yes, and on the other hand, so we should be careful that this is so this delay depends on some papers, but if we believe this delay, so I guess that so for example, we can consider such a thing. So if energy is released, so plasma should escape from this trapped fireball. It takes some time. And on the other hand, so magnetic field perturbation, Alfven wave, so propagate immediately. And then this Alfven wave inject energy to the fireball first. And so this is first comes. And later main outflow fireball comes and it releases X-ray a little bit later. So that may be a possible scenario.
So then the delay can be used to estimate the optical depth or density.
Yes, all the trapped fireball. Yes.
And the later one, it has a clear frequency dependence. I remember, so this is, so you observe it in X-ray, and then the radio should come, I don't remember, but 10 hours later. He said, okay, so now go, radio guys, you now, India, they said, okay, you 10 hours later it will happen. And they started monitoring, and there again, it was observed again.
Oh,
So it's a which one is later?
Few hours later, few hours.
Yeah, but which the radio
Radio
one,
was later.
the radio is later.
radio. So
But this one,
What
X-ray is later.
So
So are they the same type of object?
no. It's afterglow emission. Yes.
Oh.
So was it compared to the X-ray or in the radio itself? I think it was radio itself where the India had the higher frequency and then the Australia had the lower frequency. And so the frequency dependence was such that it was a few hours later. So it's not X-ray radio, but radio to radio.
Ah. So this figure is corrected by such a dispersion.
Yeah, so.
Okay, so if there are no questions, thanks to speaker again.